So not going to be a lot of coding today, which is why I decided to just go ahead and go back online. There's going to be a little bit of scripting, but not very much, and it's not really worth anything. It's stuff that we've already done pretty much in class, so I'm not gonna stress that a lot. Here at the beginning, one of the things that I want you guys to learn is kind of the basic fundamentals of why statistics works and why we can rely on statistics, because these ideas like the central limit theorem, they get applied anytime we go to make a decision about a set of numbers. So if we're doing an analysis of variance, whether you think about it or not, what you're essentially doing is you're invoking the central limit theorem as you do an analysis of variance. If you do a t-test, you're invoking the central limit theorem. If you're doing a regression, you're invoking the central limit theorem, because the central limit theorem is this idea that applies to any test statistic that we might draw from a population. And so what I want to do is make sure that you have that fundamental relationship between the statistical population, which is this big population of numbers that we might want to know something about, and how that relates down to the small sample that we take from that big population, and then how that small sample allows us to say things not only about the big population, but also about another sample that we might take from either that population or some other population, and allow us to tell whether we've drawn those samples from the same statistical population or from two different statistical populations. So that's kind of, if you can understand that basic fundamental of how the central limit theorem works and how it can be applied to a lot of things, it makes doing any statistics just easier if you can internalize that core set of I don't know, it's almost like a belief, but it's supported by theory. There's a lot of theory back in the 1950s that say that it works, but getting that idea that the central limit theorem is this Swiss Army knife of statistics that you can apply to a lot of different things. So what I want to do before we go back and revisit that, though, is explore some things about different data types. So far in this class, we've been mainly dealing with numbers, and so I want to talk to you about other kinds of data other than just numerical data. But before I get to all of that, I was supposed to do this first thing. I wanted to answer any questions you might have had about homework. I'm going to go to gallery view so I can see all of you. Do you guys have any questions about the homework assignment now that you've been working on it again? Nobody? Everything seems straightforward? Okay, whenever you're finished with that, there is a link on the Moodle page where you can go and turn it in. Please save it as a PDF if at all possible. It just makes it easier for me. You can save it as a Word file or something else, but then the first thing that I'm going to do when I download it is I'm going to convert it to a PDF, because I use my iPad typically to grade these assignments and get turned in digitally. It's just easier for me to grade in a PDF. So one or the other is going to happen. Either you're going to convert it to a PDF before you submit it, or I'm going to convert it to a PDF after I get it. And then there's a convention there for naming the files. And I like them named that way because when I download them, if everybody's just put, homework number 1, then it's homework number 1 version 1, homework number 1 version 2, homework number 1 version 3, etc. And then I have to go back and tag names on those so that when I then hand them back to you digitally, I know who I'm sending which assignment to. I struggled a lot last semester getting my first year biology students to name files in a way that it was easy to keep track of which file belonged to who. So that's the reason for the weird file naming conventions. There was a time back in the old days when every file name was limited to 8 characters, and thank God we're not in that land anymore. All right, so sounds like homework's going fine then. All right, well, good. Hopefully the last week of working on it has helped you with that. Let's share my screen, and then I'm going to get rid of all of you, put you on another screen, and get rid of stupid Zoom. Okay. Can all of you see my PowerPoint and make it out well? Is that the only thing you see on the screen? Okay, all right, good. Okay, so I guess I didn't post this. This is, let's see, where do I have it? Give me just a minute, I'll be right back. I don't see it on my shelf. There's a little book that I used when I first taught this course. It's called Intuitive Biostatistics. Oh, here it is. It's called Intuitive Biostatistics, and it's a nice little book. Actually, I like it in a lot of ways. And the reason that I chose it the first time that I taught this course was because it tries to develop statistical intuition. And so one of the things that it does is it purposefully avoids a lot of complicated equations. And after I taught it that first time, one of the most common comments that I got back in my course evaluations was, it would have been nice to have a book that actually had the equations in it. And so I abandoned the book and went to a different book, but I still like some of the chapters. And I realized as I look at this slide that this is from Matulsky chapter 8, so I'll post that. But Matulsky chapter 8 basically deals with types of variables, but it basically has the stuff that I'm about to tell you in it. But I'll put it up on the Moodle site just so you have a reference to it. Let me make myself a note to remember to do that. I've also assigned some other chapters in Matulsky early on, talking about populations and sampling theory and things like that. So if you haven't read those, please do. They're actually really easy to understand if you're having any difficulties with this material. So there are different scales of data. And so there's qualitative data and there's quantitative data. And then within qualitative data, there are two types of data called nominal data and ordinal scale data. And so nominal scale data are things that have structure, but there's really no ordering. So in the case of gender, we have gender. There's male, female, bi, trans, whatever. All of those are labels that we can put on items. And in this case, it's people, but they're not one that's better than another. Females are not better than male, male is not better than female, etc. Same thing with race, religion. You know, Protestant can't be given a level of 5, and Catholics are given a level of 4, and Buddhists are given a level of 3. They're just one religion is another religion is another religion, and they can't really be ranked in any way. So nominal data are categorical data, but they can't be ordered. One doesn't have more value numerically than another. Ordinal scale data, on the other hand, are nominal data or categorical data that can be structured. They can be ordered. So sizes are small, medium, and large. Attitudes, strongly disagree, disagree, neither disagree or agree, agree, and strongly agree. You get typical Likert scale data. Those are ordinal scale data. Now, we know that if you strongly disagree, you disagree more than you disagree, but we don't know what the actual value is of that difference. You only know that one is more strongly disagreeing than the other. If you disagree, you feel more disagreeable about something than if you're neutral about that. But once again, the scale, the distance between neither agree nor disagree and disagree might or might not be the same as the difference between disagree and strongly disagree. For example, I strongly disagree with Ted Cruz's beard and mustache. I think that stuff is just hideous. He looks terrible with it. I wish he would shave. You might strongly disagree with my goatee. But then again, I just mildly disagree with Colonel Sanders' goatee, because that's the kind of goatee that a Southern gentleman should have. And so, this is something where there isn't really a scale, except that these things are all relative to one another. Quantitative data, on the other hand, has actual numbers that have meaning. So for example, temperature. 1 degree centigrade means the same thing between 0 degrees centigrade and 1 centigrade as it does between 100 centigrade and 101 centigrade. But if we're out in nature and we are at 25 degrees centigrade, and then we move to an environment that is 50 degrees centigrade, that's not twice as hot. And so ratios don't necessarily make sense for this. In the same way that if you're at 0 degrees centigrade, which is about the temperature that I woke up this morning, and your body temperature is 37 degrees centigrade, you're not like 37 times more hot than the air around you. So ratios, dividing. So with interval scale data, adding and subtracting makes sense, but multiplying and dividing don't make sense. On the other hand, ratio scale data does matter in terms of multiplying and dividing. Multiplying and dividing do make sense. So for example, yesterday, I have backyard eggs. Or backyard chickens. I don't know if I've told you guys that yet, but some weeks we'll collect. Let's see, we collect about three eggs per day, so that would be about 21 eggs per week. But as the weather warms up, we're going to collect about 6 eggs per day, probably from the chickens in our backyard, which would be 42 eggs per week. And so we will be collecting 2 times more eggs per week as the weather warms up, because this is data that are not only interval scale. The difference between 1 egg and 2 eggs is exactly 1 egg, but also 1 egg or 2 eggs is twice as many as 1 egg. And so the test of whether you have ratio scale data is, can they be compared as multiples of one another? Does it make intuitive sense to do multiplication and division of these things? A person that's 3 feet tall is half the height of someone who is 6 feet tall. 20 eggs are twice as many as 10 eggs. So you can think of this as so ratio scale data. So lots of data fall into this class of data: count data, continuous data, lots of data that we see. But there are some data types that we will deal with, which are ordinal scale or nominal scale. And we want to have methods for analyzing these categorical data as well. So one could think about this as a series of nested kinds of data. So nominal scale is the most basic data you can have. Colors is another good example of nominal scale data. Blue versus red versus green versus yellow. Blue is not better than red. Red is not better than green. Green is not better than yellow. They're just names on things. Ordinal scale is categorical data that you can put in some order: small, medium, large. Interval scale data, like temperature, 50 degrees centigrade is hotter than 25 degrees centigrade, but it's not twice as hot, because it doesn't make any sense. If you go out where it's 20 degrees and you go out where it's 50 degrees, trust me, I've been out in 50-degree weather, in the desert Southwest in the summers, 50-degree weather seems way more than twice as hot as 25-degree weather. And so interval scale data, the intervals make sense, in terms of 1 degree means 1 degree regardless of where you are on the scale, but it doesn't make sense to multiply and divide those things. And then ratio scale data are capable of doing mathematical operations like multiplication and division on. So the thing about this is ratio scale data implies that you could have any of the lower scales of data in that. So you could take temperature, which we've talked about a little bit, and you could say 50 degrees centigrade is hot. And trust me, it's hot. You could say that 30 degrees centigrade is warm. And you could say that 10 degrees centigrade is cool. And you could say 0 degrees centigrade is cold. So what you've done is you've taken interval scale data and you have converted it into ordinal scale data. Now, what you've done is you've lost some information because while you had a number that was attached, that is now attached to hot, if you just use hot as an ordinal scale data, you've reduced the numerical values of these, and there are some things that you can't do. For example, you can't average cold, cool, warm, and hot together to come up with an average temperature, but you can take 0, 10, 30, and 50 and add those together and come up with an average temperature. So you can take interval data and convert it into ordinal data, and it still means something, but it actually means less. You can't take ordinal data and convert it into interval data. So if you were, for example, a field biologist, like I am, and you're interested in how the body temperature of lizards affects their sprint speed, for example, you could be out in the field and you could be recording temperatures of lizards that you catch, and you could classify them. Oh, that's a hot lizard, that's a cool lizard, that's a warm lizard. But if that's how you recorded your data, that's all you would ever have. You would have these relative body temperatures. On the other hand, if I take my laser thermometer and I measure their body temperature and it says it's, they're 28 degrees centigrade, well, I could determine at a later date, well, that's a relatively cool body temperature as opposed to a warmer body temperature, but I can't ever take the ordinal data and then translate it into an interval scale of data. But I can take interval scale data and translate it into ordinal. In the same way, I can't take nominal and translate it into ordinal, but I could always take ordinal and then just remove the ranking and convert it into nominal. So ratio scale data has all of the characteristics of interval, ordinal, and nominal, potentially, depending on how you treat that. But you can never convert ordinal or nominal into interval or ratio. So also recognize that if you begin with ratio or interval scale data and you convert it into ordinal or nominal, you necessarily lose information in your data as you do that. So this is an important distinction, and I'll show you why in a minute. Do you guys have any questions about data scales? Okay. I'm not a big sports fan, but one of the things that I do like to watch when it comes around is I enjoy watching the Olympics. And when you compete in an event in the Olympics, you are awarded either a gold medal or a silver medal or a bronze medal. And if you finish anywhere below that, it doesn't really matter because you don't get to stand on the podium. So what level of measurement scale are we at with medals in Olympic Games?
Ordinal.
Yes, Hannah, why ordinal?
Because you can order it by like gold, silver, bronze.
Okay, it's way better to have a gold medal than it is to have a silver medal, isn't it? And it's somewhat better to have a silver medal than a bronze medal, although everybody would rather have a gold medal. So in this case, they're ordinal, but the difference between gold and silver is possibly bigger than the difference between silver and bronze, simply because of the way that we perceive them. Well, some people would say, well, we could actually reflect this ordering and convert this ordinal data. So this is ordinal data. And we could say, well, a gold is worth 3 points, a silver is worth 2 points, and a bronze is worth 1 point. So if we converted gold, silver, and bronze to an interval scale, then we could actually analyze these with different techniques than we can analyze them if they were just ordinal. So what I've done here is I've taken three athletes in 1, 2, 3, 4, 5, 6 events, and I've recorded their performance. Person 1 is decent, but basically won a bronze medal in all 6 races. Person 2 won a gold in the 50-meter freestyle and the 100-meter breaststroke, but finished 4th in everything else. And person 3 got nothing but silvers in the 50-meter freestyle and the 100-meter breaststroke, and got silver in the 200-meter breaststroke, but finished 5th in everything else. So if we take these numerical values that we've assigned to gold, silver, and bronze, what we find is that if we add up person 1, their total equals 6. If we add up person 2, their total is equal to 6. And if we add up person 3, their total is equal to 6. So numerically, by doing this, each of these individuals is the same. Now, if you average them, take this 6 points and divide by the 6 events, that averages out to a score of 1. This averages out to a score of 1. This averages out to a score of 1. Now, if you were an athlete, how many of you are athletes? Raise your hand. Okay, 1, 2, 3, 4, 5. Whether you're an athlete or not, which of these people would you rather be? Person 1, person 2, or person 3? I see person 2, person 2. Anybody else? 2, 2, 2, 2. Why do you all want to be person 2? Numerically, these 3 people are exactly the same.
Like you said earlier, gold's a lot better than a bronze or a silver.
So this is the problem with taking ordinal data, converting it to numbers, and magically saying that we now have interval data. When we have ordinal data, all we know is that one is better than the other, but we don't have any measure of how much better that one is than the other. So gold is better than silver, silver is better than bronze. But in our perception, in this case, if we were to put these on a number line, bronze would be maybe way down here as we go from least desirable as an athlete to most desirable. It would be nice to medal in an event. It would be even nicer to get a silver medal in an event, but it's probably way nicer or way more desirable to get a gold medal. And this is one of the problems with taking ordinal data and converting it to interval scale numbers and then saying, well, this is a 1, this is a 2, and this is a, or sorry, this is a 1, this is a 2, and this is a 3, because in reality, this may be a 1, this may be a 2, and this may be a 7, because it's more desirable to achieve at that level than it is to just place second. Who wants to place second in anything? So this is the difficulty with taking ordinal scale data and converting it to interval scale data, and then attempting to do the kinds of things that we do with interval scale data that we would do with any other kind of interval scale data. So to continue this barrage of triviality, which is the Olympic Games, here we have the time in the 100-meter sprint for the 2012 Olympics, 1992, 96, 2000, 2004, 2008, and 2012. And these are the times for gold, silver, and bronze. And then these are the time differences between gold and silver and bronze. So if these were indeed interval or ratio scale data, gold, silver, and bronze, then the difference between gold and silver and the difference between silver and bronze should always be the same. Not only should they be the same within a given race, they should also be the same across races. Now, one of the things that you'll notice here when we look at these differences is they do vary. The difference between gold and silver in 1992 was 0.06 of a second, but silver and bronze were running neck and neck. They're only 0.02 of a second difference. What happened in 2008? Do you guys remember?
Usain Bolt, isn't it? Who won?
Usain Bolt ran. He set a world record at the Olympics. Not only that, he ran the 100 meters, and towards the end of the race, he was so far ahead of people, they started looking around for where the competitors were, slowed up a little bit. He would have been even faster if he had not started celebrating before the race was over. He crushed it. 0.2 of a second in a 100-meter race is an eternity. And when you go back and watch the film, so homework for Monday is go and look up Usain Bolt's 2008 Olympic 100-meter winning run. There's this chasm of space between Usain Bolt and the rest of the field. 0.02 of a second between silver and bronze, 0.2 of a second between Usain Bolt and the silver finisher. So in this case, the difference between gold and silver is huge, not only in terms of our mental perception, but also in terms of the time differential is gargantuan. This person in 2004 won the gold because that person beat the silver medalist by 100th of a second. So these ordinal data are ordinal because all that matters is that you finished in front of silver. All that matters is that you finished in front of bronze. It doesn't matter if you did that by 1800ths of a second or if you did that by 100th of a second. Or sorry, 200ths of a second. Sorry, 0.2 of a second versus 100th of a second. It doesn't matter. The difference is still one person finished ahead of another. And so it doesn't make sense to take these ordinal data and try and convert them into some higher level measurement scale of data that don't really make any sense, because they don't make sense when you add, subtract, multiply, and divide them. Not only that, they don't make sense in terms of what the real differences are between gold, silver, and bronze if we look within a single race or if we look across races over multiple years. So the kinds of data types that are ordinal that we commonly look at is when you express course evaluations. You know, was this a good course? One of the questions on the idea forms is, would you agree with the statement, this was an excellent course? And you can strongly disagree, you can disagree, you can neither agree nor disagree, you can agree or you can strongly agree. Those are Likert scale types of responses. And the way the company that runs the idea form is they basically convert these different verbal statements to numbers, and then they calculate averages on them, which makes no sense from a statistical standpoint. But then they calculate averages and standard deviations, and they try and interpret these things statistically using those things. So this first one is ordinal scale. Pounds of corn in a bushel of corn, what scale of data is that? Nominal, ordinal, interval, or ratio? Logan.
Would it be ratio?
Yeah, it would be ratio, because if in one bushel of corn you have 1.5 pounds of corn, and in another bushel you have 3 pounds of corn, you can actually say that the 3-pound bushel of corn is twice the weight of the 1.5 pound bushel of corn. And by the way, I have no idea how much a bushel of corn weighs. I think it's considerably more than 3 pounds. Colors. Haley, what scale?
Would it be nominal?
It is nominal. Yep, because one color isn't better than another color. Now we could ask you on a ordinal level scale to rank your preference for different colors, but then we're not really ranking the colors, we're ranking your preference. And so the colors themselves would be nominal. Jonathan, what about the percentage of your day that you feel anxiety?
Would that be ordinal?
It wouldn't be ordinal.
Hold on.
Okay, go ahead. Think about it for a minute.
Yeah, I don't know. I'm just gonna guess ordinal.
Okay, Blaine.
Isn't it interval? Because you can have the amount of time and like the percentage of your day you're feeling anxiety. 1 minute would be like a small percentage, but if you did 2 minutes, that'd be twice as 1 minute. So you would have double the percentage. Is that incorrect?
Yeah, so is that interval or is that ratio?
Ratio, sorry.
That's ratio, isn't it? Yep, exactly.
Yeah.
Because if you have a 24-hour day and you spend 1/24 of that day feeling anxious, which in the age of COVID, that would be totally reasonable, then spending 2/24 of your day being anxious is actually spending twice as much time being anxious. And that would suck, but that's the way it is. Number of eggs produced by individual chickens in your flock. Hayden.
Would that be nominal?
Number of eggs?
Categorical?
Well, so if I have one chicken that's producing 2 eggs and one chicken who's producing 6 eggs, how do those relate to one another?
Ratio?
That's ratio. It's definitely ratio. Yep. Number of seconds required to run 100 meters. Chance.
Does that count?
Pardon?
Count? Continue?
So it's count data. So it's at the very least it's interval data. But if you're running the 100 meter in 5 seconds and somebody else is running the 100 meter in 10 seconds, do those have a relationship to one another? Yeah, one person is running twice as slow as the other individual is. So this would be what? I just did what with the numbers?
Yeah, cat ratio then?
Yeah, it would be ratio because you can multiply and divide those things and doing that mathematical operation on them makes sense. Hannah, what about body temperature in lizards?
Would that be interval?
That's interval. Yep, exactly. For all the reasons that we talked about when we were talking about temperature before. And Samuel, whatever the next question is, you're getting the next one. So stick around. All right. Any questions about measurement scales? Okay. Cautionary note about measurement scales. This is actually from a Social Research Methods website. Read this paragraph and then give me the hands up when you're done with this paragraph. Okay, continues on the next page. Clear your hands so I can see when you're done with this page. Let me know when you're done reading. Okay, and one last little snippet. Once again, indicate when you're done. Hayden, Samuel. Okay, all right. So all of the highlighting in this passage, so this is all taken from this website at the Web Center for Social Research Methods. But all of the bolding and the color and everything is stuff that I've added because I wanted to call attention to it. What do you think about this first statement? All quantitative data is based on qualitative judgments, and all qualitative data can be described and manipulated numerically. Samuel, told you the next question would be to you.
So I guess it's just saying that those two types of data are like very related.
Okay, but what do you think about the veracity of the statement that all quantitative data is based on qualitative judgments and all qualitative data can be described and manipulated numerically?
Like, are you asking if I think that's true or?
Yes, I am asking you exactly that.
I mean, maybe not all quantitative data is based on qualitative judgments.
Okay, give me an example of some quantitative data that is not based on a qualitative judgment. Can you come up with one?
I don't think so.
Really? Somebody else give it a shot. What's an example of quantitative data that is a type of quantitative data that is probably not based on qualitative judgment? Blaine, is your hand up? Okay, well, your hand was up. So Blaine, give it a shot.
Well, so I was thinking, could it be time?
Okay, so time. Yeah. Explain
Go ahead.
yourself.
Okay,
Explain.
well, I was just gonna say, you can kind of compare it and think about it in the way of like, time always restarts and is forever going. So it's always going to be quantitative. It won't be qualitative, but it is upon a qualitative idea. So like 1 to 12. I don't know how to explain it properly, but it makes sense to me. I'm sorry. I don't know how to explain
No, that's fine. I think what you're getting at is time itself is probably an objective thing. The way we happen to have divided up time might be an arbitrary sort of decision. But that doesn't mean that time itself is an arbitrary sort of thing. I'm thinking of something a little less abstract than that. And I'm thinking of it because I have a tape measure right here in my hand. Logan.
Distance,
Okay, so what do I have right behind me?
a whiteboard.
I have a whiteboard. I'm so glad that I have this whiteboard in my office. When I moved in, it was a 4-foot by 8-foot bulletin board. I'm like, oh my gosh, who uses bulletin boards anymore? Sorry, my apologies if you use a bulletin board, but I had no use for a bulletin board. And so fall of 2020, I finally got tired. Well, no, sorry. Fall of 2019, I finally got tired of the bulletin board here, and I got the school to install me a whiteboard. And then spring of 2020 came along, and I had to start teaching online. And I'm like, oh my gosh, I'm so glad that I have a whiteboard that I can write on. So this whiteboard was sold to the college as a 4-foot by 8-foot whiteboard. So I can take a tape measure, I can plug it in over here, and I can run it to this side. And I can say, well, is it 8 feet? Oh my gosh, it's not 8 feet. I've always thought it was 8 feet. It's 6 feet, 10 3/4. Why did I think it was 8 feet? 6 feet, 10 3/4. Clearly, this is the first time that I have measured this whiteboard. Now, did I have to make any qualitative decisions about this? Sorry, I can't see you because I'm not standing in front of my computer.
No,
No, why not?
because you just read the numbers off the tape measure. You didn't have to compare it to anything else.
I just read the numbers off the tape measure. Now, I could vary how tightly I was pulling on the tape measure, and I could also have made mistakes in measurement. So for example, rather than measuring this way, I might have measured this way. And when I do that, oh, it's almost, what did I say, 6 feet before? It's 5 feet, 5 feet 11. But of course, what's wrong here?
You're not
Once again, I
measuring it
can't.
correctly.
I'm not measuring it correctly because I'm not measuring parallel to the edge. That's not a qualitative decision I'm making. That's just I don't know how to measure length in a straight line very well. So I would argue that the statement, the first part of the statement, which is all quantitative data is based upon qualitative judgments, I can think of lots of measures that I take on a daily or weekly basis as an ecologist that just doesn't apply to. I had a research student. We were, like I said before, among the things that I study the thermal biology of lizards. And one of the ways in which we do this is we have a very expensive laser thermometer, an infrared thermometer gun that measures temperature on really small scales. And when we find a lizard crawling around on a wall, we take its body temperature, but sometimes you have to touch the lizard before you can take its body temperature. And so you want to hold the lizard at the back of the body, and you want to take the temperature at the front end of the body so that you're not accidentally measuring your own body temperature as you're taking the temperature of the lizard. And the student that I was working with was a heavy set guy. He was a big guy, and he had big fat fingers, and he was consistently getting higher temperature readings on the same lizard than I was in the field. And it's because his fingers were getting in the way, and the infrared gun was measuring not just the temperature of the lizard, but was also picking up his body temperature as well. And so while we were in the field, we had to work really hard at making sure that he was grasping the lizard correctly in order to be measuring the lizard's temperature rather than a combination of the lizard's temperature and his body temperature. And so once again, that's not a qualitative judgment. That's just an effort to make sure that you're actually measuring the thing that you're attempting to measure, that you're measuring it correctly and accurately. And we'll talk about accuracy in a while. So what about the second part of this? All qualitative data can be described and manipulated numerically. Hannah.
Sorry, I was just using the restroom. What's the question?
Oh, sorry, I didn't mean to put you on the spot. Go to Chance.
Yeah, are you still talking about the first part? I'm confused as well.
No,
I
I'm still
apologize.
now. So all quantitative data is based on qualitative judgments. I would argue that that's not true. Can all qualitative data be described and manipulated numerically?
Yes, I think that's true.
What about medals in games?
If you, I mean, technically, yes. If you dope, then you get a medal.
No.
at
I
race
mean,
track.
can you take gold, silver, and bronze, convert them to numbers, and that makes sense? But I just show you that it doesn't really make sense.
But it still does in a way.
What's that?
I mean, it still does make sense in a way, though. It just depends on what you're looking at. I don't know.
So you're basically saying that person 1, person 2, and person 3 are all the same because their scores, according to the medals that they got in these 6 events, all equal 6 and all equal 1.
I just think that you can still manipulate the data to go the other way, though, as well, correct?
How do you mean?
Because then because you can manipulate the data and say that they're all even, but you can also manipulate the data and say that, you know, gold is first, silver is second, bronze is third. Am I confused? Am I wrong?
But numerically numerically these 3 people would be exactly the same. Yet when I asked you, are these 3, which of these 3 people would you rather be? You all said 2. You all said person 2. Blaine, what are you trying to say?
I was just saying, I think what Chance is trying to say is like he can skew the data to fit the manipulation. For example, like we all want to be gold because we were all told that gold's the best. So gold got
Yeah.
a 3, right? But you could technically scale it. So the gold could be higher than 3, the silver could be higher than 2, and the bronze could still be a 1. And if we did that, then you could manipulate the data. So it would look like person 2 was better than person 1 and person 3. That's just by skewing your graph. I mean, that's how I think of it.
Yep.
Is that
I've got it. Nope, that's fine. So if that's the case, then you would say that you're thinking of a place where bronze is 1, silver is 2, and gold is something like 7. But once again, if that were the case, then when we look at these differences, then there would always be a set interval between silver and bronze and silver and silver and gold. But in some cases, there's the difference between bronze and silver and gold versus bronze, silver, and gold, where these are all 100ths and 100ths versus where this difference is 100th of a second. Is that 100th of a second? No, sorry, 200ths of a second, rather. Two hundredths of a second. I can't write for whatever reason. So in one year, the difference between bronze and silver is 200ths. In another year, the difference between bronze and gold is 200ths. So this would be 2004, and this would be 2008. So in this year, the difference between silver and gold was gargantuanly huge. In this year, the difference between bronze and gold was less than the difference between bronze and silver in 2004. So does it make sense to say that these categorical values, these categorical data, have real numerical value? Is the question that I have for you. Because in this case, it kind of makes sense to think of it this way, but in this case, it doesn't make any sense to think of it that way. unless we take this scale, I guess we could take this scale and say this is gold, silver, and bronze, in which case this would be this is 0.01 faster than that, and this is 0.1 faster than that. In which case, though, you've now changed the overall scale that you're looking at. The fact that I have to do that kind of machination, and when I do that kind of machination, what happens is these things end up being equidistant from one another, whereas these things are not equidistant from one another. So my question is, does it make sense to take ordinal data, in this case, gold, silver, and bronze, and convert them to numbers and get anything meaningful out of that? The fact that you can do it doesn't mean that you should do it. So I guess my question is, should you do this? Do you get any sort of meaningful added information out of doing this? Hayden is shaking his head no. Blaine is shaking his head no. What did I say that convinced you, Blaine?
Once you converted it on the board and you explained they were the equidistant apart, and like that only really worked for the first one, it kind of, I don't know, it just kind of lined up that it doesn't quite fit right. It's going to make your data not make sense in the way of like graphing and other things like that. It just seems like it's going to become, I mean, it's a nice way, kind of a shit show with your numbers, because they won't be correct, because they'll be so different, and that'll make your data look funky. And then when you go to, explain that to your boss or somebody, that data won't be, it won't make sense to them. You won't have a way of making it understanding for somebody that doesn't understand statistics.
Yeah, so to me, it's a counterintuitive thing to go from ordinal data to interval data. It might make, in some cases, sense to go from interval data to ordinal data if you wanted to put some interval data into categories for some reason. Although, once again, I find it difficult to wrap my head around that, because in the process of doing that, you lose information in the process. But then we come to this thing at the end. What about this last portion that is in red? Hayden, what are your thoughts?
I don't really like it, because when I looked at it the first time, when we read it the first time, I couldn't even understand what the graph was trying to say.
Oh, so I just put some examples of doing what this person is doing here. So let's say you could ask somebody, how often do you get a full 8 hours of sleep? Hardly ever. Sometimes, on average, I get that. Usually, almost always, I get 8 hours of sleep. Well, what this person is saying, well, we could take those qualitative data. These are ordinal data. Hardly ever, sometimes, average, usually, almost always, and just assign numbers 1, 2, 3, 4, and 5, and then treat them as if they were interval scale data. Do you think that's a valid thing to do, Hayden?
I think maybe in certain cases, but I think in other cases, no. So maybe for the situation you just described, but in the situation we were just in, definitely not.
Which two situations are you thinking?
This situation, and then the 100-meter dash one we just did, where we ordered them.
So the fact that the categorical, the fact that the categories of gold, silver, and bronze also have ratio scale data associated with them makes it harder for you to buy that than if they were things that don't have ratio data associated with them, is what you're saying.
Yeah, and everyone's scales are different. It's kind of subjective. So like for some people, if you just brought up like let's say this was about sleeping, about getting a certain amount of sleep per night or whatever. Some people can run effectively on 6 hours of sleep, which would be their 5, and then other people can run effectively on 8 hours of sleep, which would be their 5.
Yeah. So once again, So now you're basically saying that even on the sleep question, there are actually ratio scale data behind that. So when everybody's scale might be different, does it then still make sense to just assign the difference between hardly ever and sometimes an interval difference of 1, sometimes an average and interval distance of 1? And if you are hardly ever versus average, average is getting twice as much sleep as someone who hardly ever does because there's 2 intervals between that. Does that make sense to you?
I think it makes sense from the perspective of the people conducting the test, because then it's consistent throughout. But for the people taking the test, I don't think it is.
Okay, well, wouldn't we like to have a study where it was consistent for everyone?
Yeah, but I don't think, like I said, I think it's subjective. So like you can pull out whatever you want from the data out of the test you make like this, but it's not going to be the same for everybody.
Yeah, I'm going to strongly disagree with that. So one of the problems with then kind of making these sort of subjective judgments is that 2 different statisticians could look at the same kind of raw data and come to 2 very different conclusions. The reason that people do this is they want to do things that are simple, like calculating means. And they don't want to do something that is a little more complicated, which is looking at distributions. So for example, you could basically query 20 people and you could ask them a different question. And so you could have hardly ever, sometimes, average, usually, almost always. And you could ask 20 people, and maybe 10 of them hardly ever change lanes. 4 of them change lanes sometimes. 3 of them change lanes fairly often, 50-50. Let's say that average means 50-50. And 2 of them you usually change, and 1 of them changes almost always. That's 20, right? 17, 18, 19, 20. So this is a distribution. And one of the things that you can ask yourself is this distribution, evenly distributed? Do these totals differ from what you would expect if you had 20 people divided up into 1, 2, 3, 4, 5 categories, where the expected value would actually be 4? You could also do a situation where, in my animal behavior class, I teach about something called the ideal free distribution, which is the idea. It's an idea that you can apply to animal decision making out in nature, but it's also the example that I give them in class is actually lining up lanes in a grocery store. When you go to the grocery store, the first thing you do is you look at all the lanes, and what do you typically do? Chance?
You said you go to the grocery store and you looked at the lanes, and would you?
Yeah, you look at the lanes when you go to check out.
And then see if they're busy.
Yeah, you see if they're busy. You don't go and stand in the line where there's 10 people going. You go and stand in the line where there's 2 people going. There's 2 people waiting to go through, unless you see what? Can't hear you, Chance.
Yeah, it's because I don't know if I'm right. I'm talking to myself. An empty one?
No, go ahead. So there's no right or wrong question. Just think through. If you go to a supermarket and you see a bunch of people there, you'll see some lanes are longer than others, but some lanes are longer than others because in some lanes you have people that only have 1 or 2 items, and in other lanes you have people who have a full basket, like 50, 60 items. They're shopping for the week versus people who only have a couple of items. They just stopped in because they forgot something and they're picking stuff up on the way home. You might get in the longer lane because you perceive that that lane will go faster because even though there are more people in it, each person has fewer items rather than getting in the short lane because those people in the lane with only 2 people have full baskets of groceries. Now, sometimes you get in a lane and there are only a couple of people and each person only has a couple of items. And you think, that lane is going to be the fastest. And you get in that lane and then it's this guy and he has like 10 items and he has 12 coupons. Well, he has 12 items and he has 10 coupons and he wants to pay with a check. And then he writes the checkout wrong. And you realize, oh my gosh, I got in the wrong line. I thought I was going to get in a short line because things were going to go quickly because he didn't have many items. And it ends up that he's doing a set of things. Oh, and he has alcohol and there's an 18-year-old doing the checking. So they have to wait for a manager to come over and approve your beer purchase, et cetera, et cetera. And so there's a set of rules. There's this idea that ideal free distribution, that if everybody has complete information about how checking lanes work at a grocery store, we'll distribute ourselves evenly across those lanes in a way that everybody ends up staying in lane for the same amount of time. And so when I talk about this in animal behavior, my students, when they go to the grocery store next time, they start to look at the lane process differently. They start evaluating, does that person have a lot of items or very few items? Does that person look like a person who's going to probably pay with a check? Is there alcohol in their basket and they're in a lane with a young person who is not allowed by law to check out alcohol, so you have to wait for an assistant manager, et cetera, et cetera. They start to figure those things out because we've introduced this idea of the ideal free distribution. Now, it may be that before I teach this in my class, I ask my students how often they change lanes. And this is the data that I get. And then after we teach the ideal free distribution, we get a distribution that's more like this. 5 still hardly ever change lanes. 5 do it sometimes. But now 7 do it about 50% of the time. That's 10, 17. None of them do it this way, but now suddenly 3 of them are doing it almost always because they have this new knowledge. Now I can take these 2 distributions and I can compare them to one another using a thing called a chi-square test, which we haven't introduced you to yet. It's one of the first things that we're going to introduce you to. And I can tell you statistically if those 2 distributions differ. Before they had learned about the ideal free distribution and after they learned about the ideal free distribution. Or I could assign numbers to this, say this is 1, this is 2, this is 3, this is 4, this is 5. This would sum to 10. This would sum to 8. This would sum to 9. This would sum to 8. And that would sum to 5. And I could add all those up. 10, 18, 18, and 9 is 27. 27 and 8 is 35, 35, and 5 is 40. I could take that 40 and I could divide that 40 by 20. And I could say that the average score here is an average score of 2. And I would do the same thing here. This would be 5 times 1 is 5. 5 times 2 is 10. 7 times 3 is 21. This would be 0. And 3 times 5 is 15. That's 15. 15 and 21, 36. 36 and 15 is 51. I would calculate 51 divided by 20. That's 2, 40, 110. That's going to be then 5. So this is an average of over 2.5. And I could ask myself, is 2.5 different from 2? And what I'm going to find when I do that is that those things are probably not statistically different from one another, because the amount of variation is high in both of these data sets relative to the scale that we're measuring things on. Whereas if I looked at that distribution and looked at that distribution, my guess is that a chi-square test would probably show that those two distributions are different. So when you take ordinal data or nominal data for that matter, and apply a chi-square test to it, oftentimes it's going to give you a better answer, a more correct answer, an answer that reflects the reality of the situation, more oftentimes than if you take it and convert it to numbers and then analyze those numbers as if they actually meant something. So when we talk about chi-square tests, we'll talk about this issue again. One of the other things that you should always be aware of is what's something that's weird in what is basically something put out by a Center for Social Research Methods. What jumps out at you as kind of strange in this thing? Well, we're out of time. Sorry, I ran over. We'll come back to this on Monday. We don't have class on Friday. Take Friday off, relax. Get your homework turned in by 5 o'clock today, and think about this between now and Monday. Because there's something weird on this slide that jumped out at me when I first saw this quote of information. All right, questions? All right, I'll see you guys on Monday. Hey, Blaine. Blaine's gone already. All right.